Hey there, Gregory Carlson here with the Calculus Building. Let's do some chain rule applications. So you're used to this one by now. We're going to find a tangent line to this graph, and look at this, x to the 3 minus 9x to the 10th power. If we FOILed this whole thing out, it would have a degree of 30. So that's a pretty high power polynomial. We have this point 3.1 comma 584.676, which is a point on this graph, and we want to find the equation of the tangent line at that point. So we can see it's probably going to be pretty steep, because if you plugged in a 3 here, you'd get that y equals 0, and 3.1 is y equals 584.676. So I imagine this is going to have a very steep slope. So let's find dy dx by doing the chain rule. So if I have y, okay, so dy dx is going to equal, take the derivative of the outside, so leave the inside intact. There we go. So 10 times x to the 3 minus 9x to the 9. And then don't forget to multiply by the derivative of the inside. So what is the derivative of x to the 3 minus 9x? Well, the derivative of that would equal 3x squared minus 9. So there is your derivative. Using the chain rule, we took the derivative of the outside and then multiplied it by the derivative of the inside. And now we're just going to plug in 3.1 and see what we get. So what is the slope? I'm going to call it m. So this is the slope at the point 3.1. So that's going to be 10 times 3.1 to the 3 minus 9 times 3.1. All of that to the 9 times 3 times 3.1 squared minus 9. So let's quickly figure out what this is. We've got 3.1 to the 3. So 3.1 cubed, which is 29.791, minus 3.1 times 9, which is 27.9. That's going to be taken to the 9th power times 10. Inside of here, we've got 3.1 times 3.1, which is 9.61 times 3, which is 28.83. This is going to be super steep. I can just tell. All right, so here's what we got. So 20, this is going to be 20, actually it's going to be 19.83 when we take off the 9, and 29.971, oops, I'm sorry, 29.791 minus 27.9. So we get that number. We're going to take that to the 9th power. Pretty steep, times 10. And then we're going to multiply that by 19.83. So, wow, the slope right there, and it's just going to get steeper and steeper and steeper super fast, is 61312.1399. So let's use our point slope equation, y minus y1 equals m times x minus x1. And let's find the actual equation of that. So that's going to be y minus the y point, which is 584.676, is equal to our slope, which is 61,312. I'll round that to 0.14, times x minus 3.1, which was our x point. So almost there, we're going to do the distributive property. So y minus 584.676 is equal to, sorry, move my paper a little bit. All right, this is going to be 61,312.14x minus this number times 3.1, which is 190,000. That's quite the y-intercept. You do see stuff like this with real-life applications. These crazy numbers are not always nice and calm, like a lot of the examples we've done. So it's good to be able to do the calculations even with crazy numbers. 584.676 So the tangent line right there would be y equals 61312.14x minus, and we're going to take off 584.676. And so the opposite of that number would be net minus 189,482.96. So there is your tangent line with a pretty crazy slope and a pretty crazy y-intercept. So the reason for that is because of how quickly this function is going to get steep after a value of 3. All right, I have 2 more to get through, and then we are ready to talk about something new. These ones will be a little easier, I think. The position of a particle moving along a coordinate line is s equals blah, 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 where s is in meters and t is in seconds. Find the rate of change of the particle's position at t equals 3. So again, here's a function of position, and if we take the derivative of that, we get the velocity of the particle. Maybe it's in the Hadron Collider or something, and we're going to get the velocity of that particle at all times. So we need to know what is s prime of t, what is the derivative, and again, rewrite this as all of this to the 1/2. So what we do is we're going to bring out that 1/2, leave the inside alone. The power is going to be 1 minus 1/2, which is negative 1/2. And then multiply it by the derivative of the inside. Now be careful, don't just multiply it by the first number you see. Remember that the derivative of a constant is 0, and so the derivative of the inside here would be 6. So I'm just going to box that because that's your derivative right there. This is a square root, so they may want you to move the square root in the bottom and then times top and bottom by the square root just to rationalize it, but this is the derivative, so I'm just going to leave it. You know what? Let's just show you. So this will be 1/2 times 1 over the square root of 31 plus 6t times 6. And in fact, 2 and 6 will cancel, so that'll become a 3. So I'm just going to put a 3 up here. So if you wanted to, you could rationalize this by moving the square root up into the top. Okay, let's go ahead and, so my new function is this. So let's see what the velocity is at time equals 3, so you just plug in a 3 right there. So s prime of 3, the velocity at time 3. 3 times 6 is 18. 18 plus 31 is 49, I believe. Oh, that's nice. So we're going to get the 3 over the square root of 49, which equals 3 over 7. So the derivative, the instantaneous rate of change of the particle in meters per second, so maybe we should include our units, meters per second, at that time of 3 seconds is going to be 3/7 of a meter per second. Last one. This one actually isn't really going to involve the chain rule because we see the total outstanding consumer credit of a country in billions of dollars. So this is the total amount of credit, or also known as lending trustworthiness, if you want, of an entire country. We can see that the country is growing, its economy is getting stronger, so more and more people have more and more credit. So we want to find, if I just kind of told you what the meaning of this is, we see that the credit's getting better and better, so our derivative will be getting larger and larger as this graph gets steeper and steeper. So because x is not in terms of any variable, it's going to be pretty easy to find the derivative of this. So c prime of x is going to equal 9.13 times 4, which is 36.52 x to the 3 minus 85.06 times 3, which is 255.18 x squared plus 287.26 doubled, which is 574.52 x to the 1, or just x, and then that's minus 309.12 and then this constant number just goes away. So here's the derivative of our function that we just calculated, mainly by just doing the power rule over and over. Find it in the year 2012. So this is the number of years since 2008. So 2012 then would be 4. So we're going to find the derivative right there. And so that means c prime of 4 So basically, you're just going to want to crunch that whole thing out. And that's going to be the rate of change of the credit of the country at that time. So I am going to crunch it really quick. You may want to just skip to the end of the video where I tell you the final answer. 64 times 36.52. 16 times 255.18 4082.88 plus 574.52 times 4. Oh, what's going on? Try again. 574.52 times 4 minus 309.12. So let's calculate the final answer. It's going to be 2337.28 minus 4082.88 plus 2298.08 minus 309.12. So a pretty modest increase in the 4th year of the credit of the country. So, and we see that the 4th year was kind of before it really kind of took off almost exponentially. And so there's your answer. So I hope you like the chain rule. I hope you're enjoying these application problems. And we're going to do something really cool in the next section, which is we're going to be looking at higher order derivatives. So if you found this helpful, please like and subscribe, share it with your friends, and I will see you in the next section. See you there.